Okay, we will start today's topic, which is another type of permanent magnet machine. Okay. In the last lectures, we consider that the permanent magnet machines may have a different classifications or types. One is the permanent magnet generator. Okay. Earlier there were generators for automobiles, etc. Okay. And here also the generators would be typically AC. That means you have 3 phase windings in the stator and the permanent magnet in the rotor. So, you will get a AC sinusoidal voltages generated at the stator windings, and they would be of the frequency corresponding to speed, and you can get DC out of it by having a rectification. Nowadays people are proposing that wind generators can be of permanent magnet type, because you can fix large number of magnets for low speed applications and get the required frequency, or frequencies does not matter, you can rectify it and feed it to the battery to charging the battery, and from battery you can have inverter. So, these are some of the schemes which are being envisaged. Next is the permanent magnet motors. Again we have one which are DC type of motors, where the supply is DC. When the supply is DC, either you can have a conventional commutator type of motor that will be with brushes. Okay. So, there is no difference in the performance as far as the in comparison to the conventional DC motors, because the normal field is being replaced with the permanent magnet field. Only difference is you nearly get a constant flux decided by the magnet which are fixed in the stator. Okay. So, next is invert the same one, use do not use a commutator, use electronic switching, use the converters. Okay. So, if you use the converters from the same DC source, you excite the windings in such a way that the current carried will be at appropriate time with reference to the voltage induced. Therefore, the ideal way to switch the windings is when the field is at quadrature with it. Okay. And so, these are also called square wave. So, you do not need a sinusoidal one, you can have a magnet which is nearly providing you a square wave flux density, and the windings will be also fed with a constant current from the DC source. Okay. So, the important aspect is we should be able to again sense the position of the rotor to switch what time you have to pass the current in the windings. The another variety is a conventional synchronous motor. So, or it is a sine wave permanent magnet, again is brushless motor. So, rotor will be same. So, rotor can be, in fact nowadays a lot of configurations of permanent magnet rotors, they are surface mounted. So, you have a mild steel, then you mount it on the surface, or you can have the embedded magnets, you can put it inside a ferromagnetic structure. So, it will provide the proper magnetization. So, now in fact if you go through the literature of permanent magnet rotor, there are several configurations are being tried, okay, of the magnets. In fact, you can put the magnets at and even put a cylindrical sleeve over it. Okay. So, so that it becomes a smooth air gap. So, all these things are the developments, and the fact of the matter is, since last couple of decades if you look at research papers, there are various type of configurations are tried. There are paper dealing with the different type of motors. There are also the ones dealing with the method of analysis, finite element method, methods of control, methods of applications and so on. Okay. Now, today we will look at what we did in the last class, from there we take it out. Okay. So, what recap we had a magnet in the rotor of one type, this is brushless, this is commutator type. Okay. So, we have said that here the different magnet in rotor here, magnet in stator here, windings in stator here and windings in rotor here. Okay. I think this is so it is basically a reverse mode. Only thing is, here you use commutator, here you use electronics to switch. This is what you will have. And we also said that in such machines you nearly get a constant B flux density. The air gap flux density, if you monitor, it will be nearly a constant. Okay. And as the conductors move, it is likely to give a nearly constant voltage under the BLV law. Okay. And we also looked at the converter configurations. So, we had a DC supply, VDC, and let us say these are the windings. ABC, and he said that your configurations will have different switches. Okay. And you connect to the ABC like this, right. So, at any instant how many switches will be operating? One from the top and one from the bottom, is not it? So, and these switches we said it will be a typical transistor. Okay. So, each switch will be like this. But this is a switch, is not it? Okay. Now, the sequencing, this will be 1, 3, 5, and cyclically it will be 2, 4, 6. So, it will switch in the sequence 1, 2, 3, 4, 5, 6, right. Okay. So, it could be, sometimes it will be 1, 2, 2, 3, 3, 4, 4, 5, 4, 5, 5, 6, 6, 1, is not it? Am I right? So, if it is 1, 2 means what will be the flow of current? If it is 1, 2, it will be flowing from 1, okay, going into this winding A and coming out through right, am I right? So, this is root 2. So, it will be IA will be positive and IC will be negative, is not it? So, the AC if it is 1, 2, so you can go on developing for different configurations. It is 2 3, again it will be entering through 3 and returning through 2. Okay. Then 3 4 again entering through 3, returning through 4, etc. Okay. So, it will all be depending upon which are the ones which will be excited. In the last lecture we said that if you have each phase has 2 coils, it will have a voltage induced, and the voltage induced in that winding connected in series, we said this will be the voltage which will be induced. Typically this will be net voltage induced, that is EA. That will be the sum of the voltage induced in each of the coils which are displaced by 30 degrees. So, voltage waveform is also like a rectangle displaced by 30 degrees. Okay. This is 30 degrees, right, and it is since B wave is a square wave, flux linkage wave is a triangular wave, and the derivative of a triangular wave is also a rectangular wave. So, the voltage induced will have a rectangular wave, and the currents are now fed. If this is EA, you want to feed the current IA for the A winding in this pattern. Okay. So, it is fed like this IA. This is the current, so that they are in the same, this is the peak current, this is the value I. This is how you are going to pass the currents, and each of these segments, the switches operating here is 3-2. Okay. So, 3-2 means it is minus IC and plus IB. Okay. So, this will be 3-2 is a BC, and this side is 3-4, this segment is 3-4, which will be minus this will be minus IA and IB. Then you have 4-5, 5-6, here is 1-6, 1-2, 2-3, 3-4 like this. So, these are the segments each 60 degrees, the corresponding pair of switches are operating, are closed. Okay. This is an ideal situation. Now, that means you have to switch the windings in appropriate rotor positions, that is very critical. Okay. And only supposing if your IA is somewhere displaced, then there will not be a maximum torque. Okay. So, induced voltage and the injected currents are now in phase. Okay. So, that is why we said that while this will be the voltage induced, which is proportional to the flux density, number of turns per phase, and the speed omega, so many volts, right. That is the, so it will be some constant into flux per pole into omega, okay, so much of volt, that will be the induced voltage in this. And the torque, the power that is fed into the motor will be twice E into I, because 2E is the voltage induced into I. You are aware of any DC motor, the power will be you are aware of a DC motor, you pass a current I and there will be E, is not it. So, power you always call it as E into I, that is available for conversion, is not it. That is E is the induced voltage and I is the injected current, that is for the motor. Okay. So, you are feeding current into the plus and minus. So, that is what you are doing here. So, power will be, of course, E is 2E here because E, that is the voltage per coil. So, we get from this the developed torque will be number of BG, L, R, L is the length, R is the radius into I is the current that is injected. So, this is proportional to some constant into flux into I, is not it. So, torque is proportional to flux into I and the voltage is proportional to flux into speed. Okay. Okay. Is it clear? I am just giving a simplistic view of a square wave brushless DC motor and how the switching can be done to ensure that current that is fed, after all you are feeding a current through the this is the current that you are feeding here through the converter. Okay. Current is flowing through these windings, etc. Okay. Right. So, what we have discussed is this square wave brushless DC motor, permanent brushless DC motor has a rectangular distribution of magnetic flux in the air gap. Okay. Then it has a rectangular current waveform and it has nearly concentrated stator windings. It is not too much distributed, okay, maybe 1 or 2 per phase. So, this is what is of a square wave permanent magnet DC motor. Now, the other type we are now trying to see is like a synchronous machine. In synchronous machine it is not square wave, it is not sinusoidal. So, sine wave configuration. Okay. So, it is sinusoidal or quasi sinusoidal distribution of flux magnetic field in the air gap. It is nearly sinusoidal. So, you would expect somehow that B waveform in the air gap you expect to be like this through the magnet. So, one you can call it as a north pole, another you can call it as south pole. So, you have a magnet located like this. Is not it? So, whenever at any given position the distribution of flux density in the air gap will be as is sinusoidal. Unlike in the brushless DC where you expect it to be nearly a square wave, but may not be fully 180 degrees, it may be 120 degrees also. Okay. Then a sinusoidal or quasi sinusoidal current waveform, your MMF that is produced by the stator windings. Okay. What do you expect the MMF produced by the stator winding, right, in the air gap? You excite the stator winding in the air gap. So, ideally you would expect this will also be in space, is not it, F max, and both of them are rotating a synchronism, etc. Okay. Now, if this is the MMF that has to be produced in the air gap, the current distribution should be also there. In fact, ideally, if I say the current distribution in space, that also should be this, of course this is displaced with this, it should also be ideally sinusoidal, which means you can have a current sheet. There is a concept of a current sheet. So, what you are trying to say is assume that on the surface of the stator you have put a current sheet which is where current density is sinusoidally varying in space. That will only give you a purely sinusoidal flux or MMF distribution in space, is not it? If it is rectangular, it will give you a triangular one. A current sheet in a DC motor is rectangular current sheet because there are uniformly distributed currents are there. What do you see in a DC machine? In a DC machine you are all having conductors positive in one direction, negative in the other direction, is not it? Others are all negative. So, which would mean this is a positive current sheet and this is a negative current sheet, okay, that is what it means. So, you can create in order to give sinusoidal MMF, current sheet must also be having a sinusoidal distribution of current density, right. So, that is what is the sinusoidal thing should do, okay. So, you normally have distributed windings, not concentrated winding, okay. Right. So, you have a quasi sinusoidal distribution of stator conductors, you have short pitch distributed or concentric stator winding. This you are aware of what is known as AC windings, is not it? I hope you have AC windings are different than the DC windings. AC windings are distributed windings, short pitched windings. So, these are some of the features unlike a DC winding, okay. So, this sinusoidal distribution of magnetic flux around the air gap is achieved. How do you, because you are having a magnet, therefore, you normally do some tapered magnet, okay. So, you somehow taper it in such a way that there is a more flux at the center and less flux at the edges, okay, or using shorter magnet polar, that means do not put 180 degrees magnet, 120 degrees magnet, okay. So, it is a, so you can have something like this which can be approximated to sine wave or whatever. So, quasi-sinusoidal current waveform are achieved through, now, so one thing is in a sine wave you must get flux density due to the poles as sinusoidal, MMF due to the currents to be sinusoidal, is it clear? So, these are the two things, MMF produced by the stator current must be sinusoidal, flux density produced by the rotor magnet must be sinusoidal. Now, the as far as the stator current is concerned, you must pass sinusoidal currents also, isn't it? Input current to the winding, unlike a square wave one, current going into the winding must be sinusoidal in time. So, and that is even though your supply is a DC. Say in any inverter your supply is from AC to DC. So, you know that you must have heard of the PWM inverters. So, you have a high frequency switching and you can create the currents to have a pulse width modulated, okay. So, what you do is you chop the a rectangle with varying pulse widths, okay. So, you have more width at the center, that is what you do, is not it, okay. And what do you mean by high frequency? Say this is this should be a normal 50 hertz, is not it, this time will be 1 over 50 or 1 over 100, this time, okay, 1 hour 100 seconds. Now this say what is meant by it is switched at 2 kilohertz, 3 kilohertz, what do you mean by that? What is being the, what is this frequency modulated? Huh? Huh? Yeah, switches at that high frequency. That means even when it is off, it is again switched on and off at that frequency. Huh? So you must be clear what physically it means. Okay. Switching frequency is different than the current frequency is injected frequency. Okay. So you can have a current regulated product for best possible approximation of pure sine wave. So you can regulate it to have, I mean this will be a modulation theories you are aware of. Okay. So what is it is an ideal sine wave brushless motor. So the here is the magnet, okay, and this is the displacement theta, and here is the stator. MMF or whatever you may say. So the currents, it is not a single current here. See, this is the plus minus current. Okay. What we are trying to say is this is varying, the current density is varying from 0 at the midpoint with peak at the, so it is not a single current, it is like a sheet. So current is varying, so here is 0 like that. So similarly you can say this sheet is sinusoidal. Is it clear? So it is okay now. So that means instead of putting one conductor here and another conductor here, you have spread it out into cluster of coils you can say. So I have a small concentration of coils, here is the high concentration of coils. So it is like a current sheet, you have pasted a sheet. No, this is for one phase we are talking about. 3 phase means others also will have a current sheet displaced by 120 degrees in space. This is only one phase, okay, and this is magnet of course it will rotate, okay, and at any instant of time if this is the axis, this is the, this is the, let us say the A winding A axis, isn't it, right, if this is the A axis and this is the field which normally we call it a D axis, which is changing, and this angle he calls it as alpha, right. This is the alpha, which is of course this is rotating. The D axis is the pole axis, and others are all the length, this is the air gap, other things are given here. This is the length of the magnet, okay, and this is the radius R1 at the stator, and this is theta, okay, with reference to its own axis, okay. So the turns of course you can make a 2 pole configuration or a 4 pole, I hope you know this, 2 pole or 4 pole configuration you can make. So here in this case in 2 pole it will be only one there at 180 degrees, 4 pole it is at 90 degrees. Now stator ampere distribution is sine distributed current sheet, okay. So you can represent by sine p theta because p is the number of pole pairs, okay. This is the current and ns is the number of turns, right. So this is the how the current is distributed with reference to theta, okay. and the B produced by the magnet is varying with theta as a cos p theta minus alpha. From, if you say that when d axis, it will have a maximum is B, okay. At any other, as you vary, it will be, P is the pair of poles, alpha is an electrical radiance from the axis. So, at any point it will be sinusoidal, okay. So, rotor magnet flux distribution is centered on its d axis, and d axis is displaced by an angle alpha from the axis of stator winding. D axis itself is from is away from the A axis, but D axis will go on changing with time as it rotates. Okay. The MMF, the force, see there is a, what we are trying to say is there is a current sheet which is sinusoidal, there is a B wave which is sinusoidal, okay, and force will be the whatever is at, suppose you take a small strip d theta, force on the elementary group of ampere conductors in will be in circumferential direction. So, you take a small strip d theta, how much force it will experience, okay, which is placed at a given B, right, and so it will be a product of these two B and I, is not it, BLI, length of course is there, is a BLI, is it okay. So, it is a B and an I, product B is varying with theta, I is varying with theta, okay, it will be this product. So, the torque will be whatever the force experienced into the radius, okay. So, that you will get a expression like this, okay. This constant, this will be some constant into B into I into sin alpha. B is the peak flux density, I is the current, peak current, sin alpha. What is alpha? Is the position of the d axis with reference to A axis, okay. And when will the maximum torque will be there? When this alpha is 90 degrees, okay. So, with the rotor north d axis lagging 90 electrical degrees, so you get a maximum torque. Now, with this is if the stator winding is stationary, and to produce constant torque with the rotor rotating at a steady speed, the stator ampere conductor distribution must be made to rotate in synchronous with the rotor. Of course, this you know about the basic principle of torque production is the both the field magnet B of the rotor and the MMF produced by the stator must be synchronous, okay. So, product of these two, only then a torque is produced. So, you know there is a polyphase winding with balanced polyphase current. So, you have 3 phase windings with 3 phase current sinusoidally distributed, it produces the rotating MMF, and this will be the rotating field, this is by the stator. Rotating magnetic flux distribution is known, magnetic field produced by the rotor at any omega, right. And the torque will be, I am sort of skipping the derivations. So, torque will be the, you know, the product of the B and product of I. So, the and the current is sinusoidally varying in time, okay, and then this is the B here, and this is the sin beta, beta is minus alpha, beta is the torque angle, and which is normally positive for motoring. And of course, I am just trying to pass over because you are expected to know the basic principle of synchronous machine theory. Okay. So, what it has to do is you need to have a 3 phase windings in the stator, and those windings must carry 3 phase currents, and 3 phase currents can be injected through the PWM inverter circuit from this source, and the windings also has to be sinusoidally distributed, because winding must be sinusoidally distributed and current must be sinusoidally varying in time. So, there must be, and then only you get a stator MMF which is sinusoidally varying, but rotating at synchronous speed. So, it will develop a torque which is proportional to the B, okay, and the current. So, torque is proportional to the magnet flux, magnet B and the current. Okay. Okay. Now, similarly, this is about the development of torque. Now, for the development of voltage, voltage induced, the even as a motor there will be voltage induced in the rotor, in the stator, due to the magnetic field, and which will be opposing to the voltage applied. Okay. Now, the voltage over a small strip, they normally have a, you can, another way is BLV, or you can also take it as d lambda by d psi by dt or something. Okay. So, B is varying in theta, and it is rotating at some speed, and this is B is as a function of, this is the differential for a small element. So, RMS phase EMF, you are aware, this is one term, RMS value per phase will be, it is same as 4.44 FN phi. Okay, where phi is the flux per pole. I think this is told in a different way. See, this is B L omega, omega is 2 pi f, R is of course this will be in the flux per pole, N is the number of turns here, okay, and P is the pole pairs, etc. Okay. I mean, you can verify these things. You know the flux voltage induced for each phases of the stator, and of course, you also have minus d psi by dt. I think there is a lot of confusion because some people use minus, some people use plus. I have tried to clarify some other lectures. Okay. It all depends upon, basically it is supposed to be Lenz's law. So, the voltage induced must be in such a direction to cause a current which will oppose the change of flux, right. Okay. And there are different authors interpret different way, and in the process some authors different in a wrong way. Right. So, you must be consistent with these things. So, plus minus you please check because there are typically symbols used in different journals are different, different countries are different. You see, some people use lambda for flux linkage, some people use psi for flux linkage. Some authors from British use one symbol, some authors from America use different symbols. So, now when you read these papers and books written by different authors, so you are tending to get a little confused, but then if you do yourself you will not get confused. So, the voltage per phase is omega into psi by root 2, is not it, whatever is the maximum. So, you are aware of this, so much volts. B is the flux density peak, omega is the speed, N is the number of turns, Ns. Okay. Okay. Now, so far what we are done, to sum up, we know if there is a sinusoidal distribution of flux densities and sinusoidal distributed currents, there is a torque which is produced which will be proportional to the peak of the B and peak of the current into sine of an angle, which is similar to in a synchronous motor. Synchronous motor, it is V E sine delta. V is the voltage and E is the induced voltage and the angle between them. Okay. And voltage induced is proportional to the flux. Okay. Now, there is what is a term called the inductance of a phase winding. We define an inductance. Okay. What is inductance? You have the stator winding, you pass a current, right. What will it do? It will produce a rotating magnetic field, and then whatever is the flux that is produced divided by the current, you call it as inductance. Okay. In 3 phase it is a overall, in fact the synchronous reactance, the term which all of you must have heard, what is known as the synchronous reactance. You heard this term? In a synchronous machine, the reactance of the armature is called a synchronous reactance, which is the broadly whatever is the voltage that is induced by the armature current. Say what will happen if you pass a current through the armature 3 phase, it will produce a rotating magnetic field, and that rotating magnetic field induces a voltage in each of the phases, and whatever is the voltage induced divided by that current RMS is known as synchronous reactance. Okay. And that divided by omega becomes synchronous inductance, right. I am just trying to give a physical picture. Any doubt on this, or you are confused? Clear? Okay. You are clear that I have a 3 phase winding, I pass a 3 phase current, it will produce a rotating magnetic field, and that rotating magnetic field induces a voltage in each of the phases. That voltage divided by that current will give you the reactance per phase, and that reactance divided by omega is the inductance. So, and there are people who will calculate it in a slightly different way. Okay. Okay. So in the case of so in this case, when you are calculating the inductance, you are expected to see that magnet is not there. It must be unmagnetized, non-magnetized, field is not there. So if this is calculation of armature reaction, because the term some people use, armature reaction of the armature. Okay. So you have an ideal sine wave motor, okay, and you have a pass a current through this, okay, and it will produce a flux, isn't it? Pass a current, it will produce a flux, right, and it will produce, and then if it is, it will produce flux like this, isn't it? And that flux per pole, that has to be calculated because of this current. So, okay, across each air gap, the MMF drop is equal to 1/2 of the ampere conductors enclosed. Okay. Usually how you calculate is current enclosed. What is MMF is H into G, isn't it? So, you assume what is H here, and you have the gap G here. H into G is assuming that there is no MMF drop in the iron. Okay, you pass through this, and that will be equal to H into G will be the, okay, it will be current enclosed, which will be MMF. Current enclosed will be Ns into I by 2 p into cos p theta, because it is a sinusoidal MMF at any position. It will not be same for whatever loop you take. Okay. This at any position, in some arbitrary position in the air gap with reference to some axis. Okay. Now, the gap G, right, the gap length G, what length you should take? Do you take only whatever is remaining? You say you have a magnet here, okay, and you have stator surface, Okay. Now, this is G, is not it? This is what you can. Then what about the magnet length? See, magnet is also will create certain contribution. It is not iron, right. So, one of the method is you you have effective air gap length which is given by this. First of all, G dash means you have to take care of slotting in the stator. There is a slotting in the stator, so G becomes G dash multiplied by a constant Kc which is called Carter's coefficient. Okay. Now, after this you also add, this is the length of the magnet Lm and divided by mu recoil. Okay. So, this is mu recoil is the slope of that recoil line which we discussed in the last lecture. Okay. So, this is G is
that magnet is tapered one, no?
pardon.
Magnet is tapered one, no?
Yeah, that is another problem. Okay. We are assuming you are trying to say the Lm also may vary with theta. Okay. So, I think we will take an average Lm for the purpose, right. Now, B theta will be mu naught Hg, at any position it will be mu naught into Hg. What is the B? B at any position due to the armature will be H into mu naught in the air gap, okay, and that is some Bi into cos B theta. Bi is the peak of the B which is produced by current I in the winding. Okay. So, this is caused by this current, okay, and these are some constants. Now, so what you have is you have a B which is varying in position. If you traverse through the air gap in one circle, the B varies at different position theta. Now, at any so you have to take what is the flux, integrate the flux density over the periphery of the air gap. So, fundamental armature reaction flux per pole, this is a term, so much of flux per pole. I think you are aware of this, what is the peak of the B? I think it is not a big deal, because we have said 2 by pi B into pi dl by P, is not it. So, you are aware that this will be twice B dl by P, or B dl by this P is a pole pair. Okay. So, if the B is varying in sinusoidally in space, this will be the flux per pole, it is not a big deal. Okay. Any doubt on this? So, your B is varying in the area sinusoidally, flux per pole will be average beat into the pole area. Okay. And the flux linkage is given by whatever the flux per pole 4 by pi ns, because since it is a how much flux linkage, because it is not just a total number of turns, but there is a factor which comes to the picture. The expression has exactly the same form as the flux per pole of magnet, and therefore, this is the flux linkage. Okay. Now, the self inductance is whatever is the flux linkage per unit current, is not it, divided by current, this you divide by current. Therefore, Lg will be, these are all the geometric parameters, pi mu naught ns square L R1 4 p square g double dash. So, these are all design data, is not it. See that, so that means we have an expression for the inductance of the armature winding per phase in terms of all the data. These are constants, what is ns is the design data, number of turns in each phase, L is the length of the machine, R1 the radius at the air gap, and P is the number of pole pairs, and G double dash is the effective gap length which takes care of the actual length into the slotting of the stator and the poles in the rotor. Okay. So, you have an expression for the inductance in the armature. So, the inductance calculated above is the actual air gap inductance, that is the value which would be measured with rotor stationary and rotor is unmagnetized and with other phases open circuited. That means, you do it for one phase, the winding, that is the inductance for one phase, okay. And with so you do not take care of leakage inductance from the, because you have, I hope you know, leakage inductance is when you pass a current through the winding, there will be some flux going into the leakage as well as into the slots, okay. So, you have a expression for the so called synchronous reactance. Synchronous reactance, as I mentioned, will be it will be inductance into the frequency, okay. This is a term 3 pi mu naught ns Lr 1 omega 8 p square g double dash, which will be whatever you have got the Lg expression, because you have to now take it for a 3 phase system, okay. So, I want you to understand and verify, okay, these things, because these are all available in literature, right. So, you refer to books and get this, because since since you have studied in the other machines courses, I hope you should not have difficulty in deciphering these aspects, okay. So, we have now seen a permanent magnet synchronous machine, there is a voltage induced, torque developed and inductance, and in the next class we will see how this can be used for steady state analysis of the machine, okay. We will close it here today, okay. Thank you very much.